Okay. For Friday, I've already put the video reading assignment up. We will have a quiz over the reactions we talked about today. Any questions to start with? A lot of what today was review, and a little bit of Friday will be review as well of things we've already talked about. We're still talking about ethers. No questions? All right, then let's talk about this. Ways to make ethers from alcohols. So, in terms of taking a tertiary, two alcohols, but one is tertiary or secondary, and maybe one is primary, we can put those two together to form an ether. So we just need acid as a catalyst because the two alcohols themselves are nucleophiles. So we need an electrophile in here somewhere. So what would be the first step for this, to write this reaction? Which one?
Oh, on the left.
The one on the left, tertiary peroxide. Why do you want to protonate that one?
For no hydronium ions and
Okay, so we'll make it an oxonium ion, and then the water will leave to form a tertiary carbocation. So if you have two alcohols and one of them can form a carbocation because it's a secondary or tertiary alcohol, that's the one we preferentially want to protonate. Now you might say, what about the other one? Let's do that as a second case. So I'm going to protonate that to form the oxonium ion. Since this is tertiary, I can break the CO bond, I can form water, and then I can also form the tertiary carbocation. Once I have the tertiary carbocation, then it's simply a case of tertiary carbocation plus weak nucleophile. It comes in, the alcohol adds to tertiary carbocation. I end up with another oxonium ion, and then I'm going to lose the H plus to form then the final ether. So scenario one of forming an ether from two alcohols is, what if your ether or your alcohol has, a tertiary or secondary alcohol? You're going to protonate it preferentially first and then form this carbocation. Okay, so that's one method. And you might say, okay, what about the fact that it would have the ability, let's say, to form, if you had two? What if I had two secondaries or two tertiary alcohols? What would happen there? And basically what would happen there is that we would just say, well, okay, you could protonate either one. So if you had two secondaries or two tertiaries, you wouldn't matter which one you protonate. Okay, you could protonate either one, form a carbocation, have the other one react. Okay. So that's the first case scenario, which may or may not have been something for the exam, but now it could come back on the second test. We don't want that. Right? So now, case two. What happens if they're both primary? and there is no ability to form a carbocation, what happens then? So let's say we change the reactants and we have two ethanol molecules that are going to react together with, again, an acid catalyst, and we're going to make an ether out of that. How does the mechanism change? I can't form a carbocation. So what's the first step going to be in this mechanism? I have oxygen species and an acid. The first step is to protonate the oxygen, right? Which one? Don't matter. So I'll protonate the one on the right. What will happen then? What will happen then is that I'm going to switch the molecule around, I guess, so that it looks like this. There's my oxonium ion. Will the oxonium ion leave? Will the water leave? Not, and get any points for it. Right? Because can't form a primary carbocation. So what happens next? What happens next is that the other ethanol molecule comes in and it attacks this carbon and then kicks the water off. Okay. So the other ethanol will come in and we will do what kind of mechanism? SN2. Let's show the transition state for this SN2 step. The transition state is going to look something like this. Carbon, dotted line to the water that's on its way out, dotted line to the alcohol that's on its way in. The carbon is an ethyl, so again it's going to be trigonal bipyramidal. There'll be a methyl group, there'll be two hydrogens, and so there is part of the transition state for this SN2 mechanism. So I'm showing the bonds that are being broken and the bonds that are being made. This bond being made and this bond to the oxygen being broken. Here's my question. What charges should go on the oxygens?
Both should be delta positive.
I hear they both should be delta positive. Do we agree or not? Well, let's write it in and see what happens. I can always erase. So let's write the products. What are the products of this reaction going to be? They're going to be the CH3, CH2, the protonated ether that I just formed with now two ethyl groups on either side, and I will get water as the leaving group. So there are my products. So why are those two oxygens delta plus, or are they delta plus to begin with? Let's just do a refresher in case you've forgotten that. So what do the partial bonds represent? The partial bonds represent the bonds that are being broken and made, but it's also an average. So here I've got an oxygen-carbon bond not formed. Over here I've got an oxygen-carbon bond formed. What's the average? Dotted line. Oxygen-carbon bond formed. No oxygen-carbon bond. What's the average? Dotted line. So the dotted line basically represents either the average bonds or what bonds are being made and broken. Charges, we do the same thing. We say, okay, this oxygen 0, this oxygen now +1. What's the average? Delta plus. This oxygen delta plus. This oxygen, which is the water oxygen, is 0. What's its average? Delta plus. Okay, so this is, it looks like it's a strange transition state because it's got 2 delta positives, but that's what's happening. So that's what the transition state for this would look like. It's an SN2 mechanism. Why? Because I'm using 2 primaries and I can't lose water because I can't form a primary carbocation. Julia?
Will the carbon get delta negative at all or no?
Well, that's good. It will not be delta minus because that's not going to happen. So normally it's delta plus, right? So in this case, it's going to be less delta plus. But you'd already see this is, if it's a little bit delta plus, all that means is it's a high energy transition state. And what does that mean? That means that this reaction isn't going to occur at room temperature. I'm going to have to heat it. Because I'm going to have to basically overcome whatever energy barrier there is with this transition state. So I'm going to have to heat it regardless. Right? So it's an SN2 mechanism. Does that make sense to everybody? It should. Because you've allegedly done this before. In lab last semester, the mechanism to form the dibutyl ether, which was a side product of our SN2 reaction of converting the butanol to the butyl bromide, had this as a potential side product. And that was the mechanism by which it went. So we can make ethers from, the point of this is we can make ethers from alcohols. We just have to realize that we need an acid as a catalyst. Without the acid, there's no electrophile. And basically, we're not going to form a carbocation. So it'll be SN2. So everybody kind of okay with that? The other one, if you have a secondary tertiary, protonate the water, protonate the OH, make water, lose it, and then form the carbocation. That's going to be SN1. Okay. Now, I think somebody asked before the exam on Piazza, and again, if you're not looking at Piazza, you are missing really good, you missed some really good stuff if you're not looking at Piazza. I have the ability to see who's never signed up either. So I also have the ability to see who's looked at stuff the most, and I very rarely ever do that because, quite honestly, but if you're not, you're missing good stuff. Unfortunately, you already missed it. So let's the next exam is what? The end of the month before spring break. So it's not that far away. Anyway, so somebody said, what about the difference between equilibrium arrows and arrows going forward? This is a perfect example of, will you take points off? Well, no, I'm teaching a substandard organic class. If you took this at Kent, they would take points off if you had the wrong arrows. But let's talk a little bit about what does that mean. So all equilibrium arrows mean is that the step is reversible. So in each one of these steps, every one of these turns out to be an equilibrium reaction. Right? Every one of those is a reversible reaction. Think about this. Oh, wait, I never wrote the final step, did I? Break OH bond, give the pair of electrons back, equilibrium, lose the H plus, and form diethyl ether. And if it'll be clear once I grade all the exams how many people I may come back probably on Monday if I don't get them done by Friday, and the odds of that are pretty low, but not zero, but pretty low. I'll at worst have them through on Monday. make sure your arrows go in the right directions. They always go towards the, in this case, it'll go towards the positive charge. They always move towards the delta or the positive charge. So in this case, every one of these is an equilibrium step. Think about this. If I took ether and I added acid to it, what would I do? I would protonate the oxygen to form that. Can this alcohol leave from that CH2? No, because that would be an SN1 mechanism. But can water come in and attack one of these carbons and kick off the alcohol? Yes. So it could go back here. What about here? I could lose the H plus to get me to the alcohol. So every one of these is a reversible step. And so they really should have equilibrium arrows. So there's no step here that is absolutely 100% in one direction, but not in the other. And so what that means is this is the reaction by which you take ethanol and you make diethyl ether for it that we use in the lab. So somewhere there's probably multiple plants that are taking ethyl alcohol and they're making diethyl ether out of it. And it's a fairly simple reaction except that equilibrium. So how are we going to push the equilibrium from alcohol to form ether? What they do is they basically have a continuous process. They pump in ethanol. This is a catalyst, right? Because it's being used and being regenerated at the end. So you put in some sulfuric acid, and it has to be sulfuric acid, can't be chloride, can't be HCl, right? Because we don't want the Cl minus coming in and forming a halide. So something like sulfuric acid, it's going to stay there as a catalyst. We pump in the ethanol, we heat this reaction mixture up to something in between the boiling point of ethanol and the boiling point of diethyl ether. So what happens as this reaction forms ether? The ether boils off, we collect it, we pump in more ethanol. We're basically using Le Chatelier's principle to remove the product as it's formed. So it's a relatively straightforward process. We just keep adding ether and we keep taking off, we keep adding ethanol, we take off the diethyl ether. Right? We just need a round bottom the size of this room. I've only ever heard of one place where they had a round bottom room sized. Graduate student came back, one of my friends, and he's like, this place had a round bottom as big as a room, and I'm like, really? It was awesome. In those days, we didn't have cell phones for pictures. It would have made a cool picture, but you don't need a round bottom as big as a room. You just need a big steel tank, probably with glass on the inside. So that's how they make a diethyl ether in an industrial type process. Right? So we use Le Chatelier's principle. We use the boiling point difference. Ethanol boils at 78. Ether's like 30 something. So if I raise the temperature up to 60 degrees, it's not going to boil the ethanol. It's just going to boil the ether. So we can get the reaction to go. That's where they'd be a chemical engineer and you can figure out exactly what process temperatures and all of that stuff goes into. So you make the ether, but don't blow up the plant. It's always the general rule. So that's another way to make an ether. So we've talked about, what methods have we talked about making ethers? Williamson with alkoxide and halide. We've talked about taking like a tertiary halide and adding an alcohol to it. We've talked about a tertiary secondary alcohol with another one, and then this would be two primaries. So we can make ethers a number of different ways. But basically they're all SN1 or SN2. Okay, so that's the method to make ethers. Does that kind of make sense to everybody? At some point I'll put together maybe a mechanism type take-home. I still have a category for take-home problems, so graded take-home problems, so I may do that to practice before the next exam. Okay. So that's how we make ethers. Now, the rest of the chapter is about reactions of ethers. Unfortunately, ethers are very unreactive because they make great solvents. So you think about, what ethers have we used in lab? We've used diethyl ether. How did we use it? As an extraction solvent, right? Water insoluble, low boiling point to rotary evaporate very nicely, and relatively inexpensive. Okay, it has some drawbacks. Ethers always have drawbacks. So they will undergo 3 different reactions. So let's start with reaction number 1. I take diethyl ether, I react it with oxygen. I probably need a spark or a flame. And what happens? Or, which is what kind of reaction? Combustion. And so what are the products of any combustion reaction? Of carbon and hydrogen and oxygen? CO2 and water. Technically, a metal reacting with oxygen is also a combustion reaction. Well, it's really a redox reaction. So is a combustion reaction a redox reaction. That would make a good practice of calculating oxidation reduction, or calculating oxidation numbers. I guess I forgot that. Oopsie. So we make CO2 and water. So the problem with ethers, and particularly diethyl ether, is they're very flammable. Somebody asked me after class this morning, apparently in a gender study, they talked about using ether to give to women who are childbirthing. The fact of the matter is they gave it to everybody because ether was like the original anesthesiology material. I mean, that's what it was. It's a little more sophisticated nowadays than just taking a rag. Maybe you'll wake up, maybe you won't. You're basically kind of just asphyxiating somebody, right? I mean, that's kind of what you're doing. But ether was used that way. The drawback is it's highly flammable, so that it does have that drawback. In the lab, it has a drawback that it is also flammable. So one thing that I cautioned against in lab was never, ever, ever take a beaker full of ether and put it directly on a hot plate, or you will have a fire, guaranteed, because the vapors are heavier than air, so they'll come out of the beaker, go down on the hot plate. All they need to do is find an ignition point, and then the flame goes back up into the beaker, and you have a fire. And then you tip the beaker over, and the ether flows across the hood, going whoosh with the flame, and same thing happens with ethyl alcohol, which is why we always use a water bath to heat those ether, methanol, and ethanol, because they're highly flammable. So we have to keep it away from that. In the old days when we didn't have hoods, which was the old building, I never saw this because I would never do this, but they used to take tubes and put on their container and then vent the ether down to the floor. Because apparently there was nothing on the floor that would ignite. But on the bench top, lots of stuff to ignite. So if my reaction's over there, the ether vapors flow all the way over here, ignite, and then whoosh, all the way back. So we have to be careful when we use ethers. They will combust. Some ethers are used as fuel additives. This is tertiary butyl methyl ether, which is sometimes TBME, it's abbreviated with. It's one of those oxygenates that they add to fuel in the wintertime. Sort of cut down on CO2 emissions from your car. Problem is it gets loose in the gas station and goes into the soil, and then we have contaminated soil, and we've got to somehow find that contaminated soil. So, and we don't use it in labs simply because it doesn't have an agreeable smell. So it's a lot safer than diethyl ether, but we've never switched over to it. So first reaction, combustion, helpful if I want to burn things, not helpful if I want to make bigger molecules. Actually, ethers aren't really good for doing reactions with. They're great solvents because they very rarely react. They won't react with Grignards. They won't react with organolithiums. They're the solvent of choice. However, they do have this issue. Over a long period of time, the ether will react with oxygen gas, and it will form what are called peroxides, an organic peroxide. So what is that? Well, oxygen has a diradical form. And we know that because oxygen, there's the form of oxygen that is paramagnetic. So if I pour liquid oxygen through a large magnetic field, you'll see the oxygen stream get deflected because it gets attracted to the field like all paramagnetic materials are. Paramagnetism from general chemistry means you have unpaired electrons. Diamagnetic is when you don't. So oxygen is paramagnetic. So that means it's a free radical. There's a free radical form of oxygen. And what the free radical form of oxygen likes to do is abstract hydrogens. So what happens is the CH bond cleaves so that the unpaired electron of the oxygen pairs up with the hydrogen. If I break the CH bond and give the H a dot and the carbon a dot, the H dot pairs up with the C dot. Sorry, the H dot pairs up with the O dot, and I form an oxygen-hydrogen bond. It's said that the oxygen is abstracting the hydrogen from the carbon. And that's what radicals do. So then what do I get? I'm going to get an oxygen, well, I'm going to get this. I'm going to get a carbon radical, and I'm going to get a oxygen radical, but now I've got a hydrogen on one side and then an unpaired electron now still on the other side. So hydrogen peroxide is H2O2. This is basically a half of a hydrogen peroxide because it still has the oxygen as the free radical. This always removes the hydrogen next to the oxygen in an ether. And if you wanted to, you could think about, can I write some resonance structures, where I might take these lone pairs and use them to write resonance structures? I could. So then what happens is this oxygen radical and the carbon radical then pair up. So one end of the oxygen comes in, abstracts the hydrogen, the other end of the oxygen then kind of turns around and couples back together again. And so when it does that, it forms an ether peroxide. And so that's an ether peroxide. An organic peroxide has an R group on one side and either an H or another R group on the other side. So ROOR is an organic peroxide, HOOH is hydrogen peroxide. So over time, and particularly in glass bottles, if you have diethyl ether, it can form these peroxides. Now, what do I mean by over time? More than a day or two. And glass bottles were particularly a problem because they didn't prevent the peroxide from being able to be formed. So I've only ever seen guys come in spacesuits one time to get an old bottle of ether from somebody's lab that had been there for more than a year, probably like 20 years. And they came in and they carefully in their detonation suits picked it up, put it in one of those big metal cases that they put bombs in, and they walked it, I think they walked it across, I would put it on a carton. Well, we didn't have robots then to drive it, across the parking lot to the bomb detonation truck that they took it somewhere. So I we just watched them walk across in their spacesuits with the old bottle of diethyl ether. Because the problem with the peroxide is if you want to make something that explodes, basic, explosion making 101 is that you embed a gas molecule into that molecule. The peroxide has an embedded oxygen gas molecule. So we take a solid and we turn it into a gas. What happens? There's probably some heat involved. There's a tremendous expansion in volume. With then the heat plays with the gas laws and make it expand even more, and that's what makes it very explosive. Something that goes from a small volume to a big volume very quickly. Right? So that's what happens with the peroxide. So if you saw an old glass ether bottle with a lot of solid at the bottom, you just turned around and walked out and carefully shut the door. Because these could both detonate by heat or by shock, right? So you go to pick it up, and you always pick it up with the hand you don't necessarily write with, just in case that hand isn't there when it's done. So you unscrew the bottle, and there was solid on the inside of it, on the cap. So I haven't heard of this being an issue where somebody's just found a random bottle, but there was a time when you would see those around. But fortunately not anymore. In lab, we used the silver bullet bottles. They actually kind of freaked out one day when I saw that they were selling it in glass bottles. So trauma. But the silver bullet bottles, they actually have something in them that prevents the peroxides from forming. But we still actually have to test for peroxides. There's a piece of paper, a test paper you could dip in, and if it turns blue, it's got peroxides. You dump in some iron, and that usually kills it. But ethers form peroxides very easily. This is basically a primary carbon. If it was more than a primary carbon, if it was a secondary carbon, it would be an even worse situation. So if you had something like diisopropyl ether, it would be very easy for oxygen to abstract that hydrogen, because now I form a secondary radical much faster. Years and years and years ago, I got a call from one of our chemistry graduates who was teaching high school. I think it was at Riverside. He's not there anymore. He's like a superintendent of a school district. It's just like, I knew him when there's a lot of maturity happens when people graduate. So he's now a fine, upstanding citizen and teacher. But there's always hope, right? So he called, he goes, we have a bottle of diisopropyl ether. And I'm like, can you see it? And he's like, yes. And I said, walk out of the room very carefully and don't touch it, because it's more than likely it's going to have some peroxides in it. So he's like, oh, my colleague, unscrewed it and dumped it out. And like, does he still have a hand left? Oh, yeah. And I said, tell him he's lucky and stupid, because these things tend to form peroxides very, very easily. So one thing we do if we have any ether, like if I have ether in could I have ether in my fridge that's been there a while? I might. But it's in a steel bottle, so I would immediately check it by taking the cap off with the hand I don't write with, and then dipping it in and seeing if there's any peroxide, and then adding something to it to kill the peroxides. So we have to be careful of this. I do remember in graduate school, a guy across the hall was rotary evaporating something, and we think that the brown bottom exploded, hit a piece of glass in him right here, and he had regular safety glasses on. Took a chip out of the glass. It would have taken a lot more if he didn't have safety glasses on, which is why I always say around the rotary evaporator, you gotta have your goggles on. So that was, we thought, because the ether had peroxide. So these are both of these are bad reactions, but they're side reactions that ethers can do. And they're part of practical chemistry that we have to keep our eyes open for. So ethers form peroxides very easily if they're allowed to sit for long periods of time. But what can you take away from this? It's a free radical mechanism. How do you stop the free radical mechanism? Remember, free radical mechanisms are radical reacts and what forms on the other side. Unless it's a termination step where two radicals are coming together, one radical leads to another. So that's the problem with free radical reactions, is they keep making more radicals and keep continuing on. How do you stop that? Well, you try and terminate it. The other thing you do is you take a molecule that has a hydrogen that the radical can remove, and it will make a very stable radical that will stop the process because it just makes that radical and it says, I'm stable, I don't need to go around reacting anymore. And those are antioxidants. So a phenol, because once I form the radical on this oxygen, I can form lots of resonance structures. Once you take a phenol type molecule and you use it as an antioxidant, once the oxygen or whatever free radicals in your solution or in your solid, once it deprotonates the phenol, it stops the process because I just now made a very nice, stable radical. Those kinds of things are in vitamin E, which is an antioxidant, nutrition-wise. Those kinds of compounds are added to food to keep them from antioxidizing or keep them from oxidizing as antioxidants. There's things like BHA and BHT that are antioxidants. But that's the basics. How do you stop a free radical reaction? Give it a molecule that once it forms a radical, it's stable. Right? Do we have free radicals inside of us? We're breathing oxygen. The only way to stop that from happening is not to do that, and we don't have a choice. Right? So there's part of oxygen that's going to have a free radical character. So that's a little bit about we'll probably talk about that a little bit later and some other stuff. So it's these antioxidants are not only what you're supposed to take, for good nutrition, but also they are in food and they are in the ether to help protect them from doing oxidation. Okay. So that was reaction number 2. So they burn them or explode them. Number 3 is a little bit more somewhat useful, but it's going to be review reactions. So I think that is the starting point on Wednesday or on Friday, which is ether cleavage. Okay. So that third reaction I may introduce it, but otherwise it'll be for Friday. Now, what was the other reaction that we were going to talk about? I am slowly, silyl ethers, which was a topic for today. And I know in the video that free radical halogenation was there, but in my class we talked about it last semester, in Dr. Kwan's class I also believe he talked about it last semester, but it was in that video if you need a refresher. Silyl ethers. So what's the context for silyl ethers? I will give you, let's see. I'll give another example. I would like to convert this aldehyde alcohol into a ketone aldehyde. Now, in real life, when you're doing real life synthesis, you're not dealing with a molecule that has a single functional group. So far, what have we dealt with? Only molecules that have a single functional group. Probably another reason why this is a substandard organic course. But let's talk about what would happen, the beginnings of how do you deal with molecules that have multiple functional groups. Because that's what synthetic chemists face all the time. I want to do a reaction on one part, but I got to make sure that my reagent doesn't affect the other part. So what reagent could I use for that transformation? Anybody have any ideas? I'm not going to humiliate you. Julia? H plus H2O. No. But that's a place to start. But we'll end there.
Do you like trying to form a double bond and then there'd be a enol with one ketone?
That's an interesting way to approach it, but I don't think that'll work either.
Is this like the PCC and form and that stuff?
That stuff. Yes, that is that stuff. Which one would you use? You gave me PCC. You gave me PCC and CAMN04. Which one you want?
It's oh. Wouldn't either work since it's a second meter?
No. You got to make a choice. PCC. Sarah, do you agree? Now I'm getting the looks like, what are they talking about? So, okay, you're stuck. Let's say you're stuck. Hypothetically, let's say you're stuck on this. When I ask the question, like, I have no idea. All right, let's do some basics on this. What's the difference between those two molecules? I'm turning a secondary alcohol into a ketone. Right? That's the only change I'm making. Or that's the only change I want to make. Okay? What kind of reaction is that? So I'll give you 4 choices. Bless you. SN. It's an SN1 or SN2 reaction. Yes or no? Am I substituting for anything? No. So it's not SN. E. What do E reactions produce? What kind of double bonds? Carbon-carbon double bonds. Is that an E reaction? No. Acid-base reaction. No. Right? I'm not. Am I losing a hydrogen? Well, yeah, but I'm losing 2 hydrogens. Right? I'm losing this hydrogen, and I'm also losing that hydrogen. So what's left? Oxidation reduction. What's this? Oxidation, because I'm losing hydrogens. So this is an oxidation reaction. So we're going to start building in these reactions or start thinking about these transformations if you get stuck. Question number 1, what is different about the 2 molecules? Can you put it into one of those 4 classifications? And if you can you then name a reagent that goes with that? So if this is a reduction reaction, what reagent, or sorry, this is an oxidation, I did reduction. No, did I do reduction? No. Oxidation, I did oxidation in both cases. This is an oxidation reaction. So what kinds of reagents do oxidation? PCC, KMNO4, the chromiums, Des-Martin, Swern. These are my collection of reagents for oxidation. Now in this specific case, what reagent can I use that will oxidize the alcohol but not oxidize the aldehyde? PCC. So if I want to do this in one step, we could use PCC, or we could use Swern, or we could use the Des-Martin periodate. What can we not use? KMNO4, because what would happen if I tried to do this reaction with, well, what would happen if I tried to do this reaction with KMNO4? I'm going to convert the aldehyde to a carboxylic acid. Am I going to make the ketone? Absolutely. But what else am I going to make? Carboxylic acid. That's not what I want to do. So that's an example of being selective in terms of the reagent, using a reagent that only reacts with one but not the other. Okay? So I'm trying to do this reaction. I go down to the stockroom. First of all, there's no chromium-6 because I want to be environmentally friendly. I don't have the desmartin periodate, and I don't want to mess with DMSO because it'll go through my skin and I'll be tasting garlic all day. And whatever was in the DMSO will go through my skin into my bloodstream, which is never a good thing. So, and how do I know? We've had DMSO go into our bloodstream before. Anyway, I don't have those reagents, but I got tons of KMNO4. So, what do I have to do? What I have to do is a general scheme called protection. So what I would like to do is I'd like to protect the alcohol from being, boy, I completely screwed this up, didn't I? I did. Okay, new problem. New problem. I want to do that. Now what do I need? KMNO4, but what's KMNO4 going to do? It's going to take the secondary alcohol and make a ketone out of it. I don't want to do that. So the first example I showed you was a way we could think about using a reagent that was specific. Forget about the fact that I'm trying to use that for the second one. I want to use this one for the second one. Now what I'd like to do is react the aldehyde without reacting the alcohol. So KMNO4 won't do it. So what I'm going to do is I'm going to protect the alcohol and make sure it doesn't react. That's called protection. How am I going to protect that? I'm going to use a chlorine attached to a silicon with 3 methyl groups on it. That's called trimethylsilyl chloride. So the reaction here is going to take the H and the Cl, and I'm going to lose it. And so this reaction looks an awful lot like taking a tosyl chloride, where the chlorine was attached to the sulfur, and losing HCl to bond the oxygen to the sulfur. So if I do this reaction, I'm going to lose HCl, and I'm going to form now the oxygen attached to the silicon. And now that is called a silyl ether. So this is what's called protection. I'm going to protect my alcohol so that it doesn't react any further. So once I form this silyl ether, it will only react with one thing, and that's not KMNO4. So now I could say, okay, I've protected my alcohol. Let's go ahead and react this with KMNO4. The silyl ether does nothing, but my aldehyde now becomes a carboxylic acid. So I've oxidized the carboxylic acid, but I protected the alcohol from undergoing oxidation. That's great, except I got to get the silicon back off. So the way you get the silicon back off is you use fluoride. Fluoride, and that has to be dissolved in water. So what happens is you basically make a trimethylsilyl attached to a fluorine. So the trimethylsilyl fluoride The reason for this reaction is a silicon fluorine bond is one of the strongest ones that we know of. So when you add fluorine into the mixture, it strips the silicon right off. And then we put a hydrogen back on. So that step would be what we would call the deprotection step. So your first strategy when you're faced with a molecule with multiple functional groups is just choose the right reagent, but you can't always do that. So the second step is undergo some sort of protection, deprotection scheme,
Sorry.
and then it will. There's no class in here afterwards, as far as I know, particularly on a Wednesday. So that's how you do it. And we'll talk about other protection and deprotection schemes, but this is our first example of a way to handle multiple functional groups. Okay, so that was like really the big topic for today, but that's all it is: protect, deprotect. So the reactions we've talked about today will be the ones for Wednesday's or for Friday's quiz. I'll send out an email with exactly one. Somebody will put up a question on Piazza. Can you give us some practice problems? I already know that's coming. Feel free to put it up there, but I will put together some practice problems hopefully tonight, so that way you get a little bit more practice. Remember, there's always practice problems in Top Hat as well. So if you have any questions, email me or put them up on Piazza, and we will go from there.